Just as we could predict two simultaneous discrete phenomena using a joint distribution of two discrete random variables, we might want to predict two simultaneous continuous phenomena using a joint distribution of two continuous random variables. In this case, it's convenient to extend our previous model for probability of continuous random variables from the plane into space. So previously, when we had one continuous random variable, we used probability equal to area of some region A over area of some region S, where these are regions in the plane. And if area of S is 1, we really just need area of A for our probability, and usually this requires one integral. Now let's extend this to two continuous random variables. So now we're going to let probability be volume of A over volume of S, where these are regions in R3. And again, if the volume of S is 1, we just need to compute the volume of A. And usually this requires two integrals. So more generally, I guess we could want to predict n simultaneous continuous phenomena. In that case, we'd still be using volume, but it would be an n plus 1 dimensional volume. So these would be in n plus 1 space. And we would use n integrals. All right, let's go back to just two phenomena for the moment. So for two random variables, usually the region S is the region in R3 under a surface z equals f of xy and above the xy plane. Which we could also call z equals 0. And usually this region as volume 1. Now if predicting x and y is like choosing a point at random in this region S, let's say the point is x naught, y naught, z naught. And recording the coordinates, just the first two, x naught, y naught, then we're going to call f of x, y the joint probability density function of x and y. So then we have the probability that x is between, say, A1 and A2, and y is between B1 and B2, is equal to the integral as x goes from A1 to A2, the double integral actually. Y goes from B1 to B2 of f of x, y, dy, dx. So this integral gives the area of the region I called A. Now we define the joint cumulative distribution function of xy to be capital F of xy which is the probability that x is less than or equal to this value little x and y is less than or equal to this value little y. And we can get that by taking an integral. Let me use dummy variables s and t. So t is going to go from negative infinity to y, and s is going to go from negative infinity to x. So by this integral definition, well, if capital F is the double integral of little f, then little f is the double derivative of capital F. So we take partial derivatives of capital F with respect to x and y to get the joint density function. Now we can also get the marginal density functions of just x and just y from the joint density. Let me write f capital X of x is the marginal density of x. So we take f of x, y, and we just integrate away all of the y's. And of course we could do the same thing for y. If we just want the density function for y, then we just integrate away all the values of x, f of x, y, dx. Alright, so let's do an example with a joint density function and compute a couple probabilities and compute the marginal densities of x and y. So let's consider f of x, y equal to 2e to the negative 2y e to the negative x if x and y are greater than 0 and 0 otherwise. So let's first check that this is a probability density function. E to anything is positive. So no matter what x, y we plug in, we're going to get something positive. So we really just need to check that the volume underneath this surface and above the xy plane is equal to 1. Now we've got exponential functions here. Let's just recall that if we take the integral from 0 to infinity of an exponential function of the form k e to the minus kx dx, that's equal to 1. And this is the exponential probability density function for one random variable. So we've used that a bunch of times and we know that that's 1. So we don't need to do an improper integral every time we see this. We know that's 1. Alright, so let's see that this is actually a probability density function, that its integral is 1. So we have the integral as x goes from 0 to infinity. We can start with 0 because this function is 0 for x less than 0. And y from 0 to infinity of 2e to the negative 2y e to the negative x dy dx. Alright, so if we're integrating dy, this e to the x is just a constant. It can come out, at least out of that first integral. 2e to the negative 2y dy dx. Alright, now what's in parentheses here is just an exponential probability density function. So we know that that is 1. So that leaves us with the integral as x goes from 0 to infinity of e to the negative x dx. And that's another exponential probability density function with k equals 1. So that's 1. Alright, so this is a two-variable probability density function. Alright, now let's use it to compute something. Let's find the probability that the variable x is greater than 1 and the variable y is less than 1. So if we do this in the same order, let's say the y integral first and then the x integral afterward, we want the integral from 1 to infinity of x, and then the integral from negative infinity to 1 for y, but we can get away with saying 0 to 1 because of the way this is defined. So the integral from 0 to 1 of 2e to the negative 2y e to the negative x, and I might as well write the e to the negative x out here because it doesn't have any y's in it, dy dx. Alright, so let's do this integral on the inside first. x is going from 1 to infinity. Alright, so this is, so I guess we actually have to integrate that. So we've got, let's see, e to the negative 2y dy. I kind of wish this was a negative 2 dy, so it would be e to the something d something. There is a 2 here, but I'm lying if I say minus, so let me put minus on the outside. Y is going from 0 to 1. So this is the integral from 1 to infinity e to the negative x. Negative, the integral of e to the something d something is just e to the something. And this is evaluated from 0 to 1. So we have negative e to the negative 2 times 1 minus negative e to the negative 2 times 0, which is the integral from 1 to infinity e to the negative x. E to the 0th is 1 minus e to the negative 2, so 1 over e squared dx. Alright, now this is just a constant, so we can pull it out. Alright, now here's another integral that comes up pretty often. If we're integrating from a to infinity this exponential density function, ke to the minus kx dx, then that's just e to the minus ka. So here k is 1, and we're integrating from 1 to infinity. So we have 1 minus 1 over e squared, e to the minus 1, 1 times 1. So that's 1 over e times this. So 1 over e, I guess we can write this as e squared minus 1 over e squared times 1 over e. So we have e squared minus 1 over e cubed is the probability that x is greater than 1 and y is less than 1. Alright, now let's ask another question about the same probability density function. Let's find the probability that x is less than y. So we have 2e to the negative 2y e to the negative x. So let's integrate as x goes from 0 to y. So x is less than y, and y goes from 0 to infinity. So we'll integrate dx first and then dy. So this equals, let's see, if we're integrating x first, the 2e to the negative 2y can come out of the x integral. Let's see, what's this inside part? This is negative e to the negative x as evaluated from 0 to y, which is negative e to the negative y minus negative e to the negative 0, which is 1 minus e to the negative y. Alright, so if we put that in here, we'll multiply that with 2e to the negative 2y and get the integral from 0 to infinity 2e to the negative 2y 1 minus e to the negative y, which is the integral of 2e to the negative 2y minus 2e to the negative 3y dy. So we can separate these into two different integrals. The integral of 2e to the negative 2y, which is easy, we know that's 1, minus 2 times the integral of e to the negative 3y dy. Now that would be easy if there were a 3 right here. So let me put a 3 here and divide by 3 on the outside. So we have 1 minus 2/3 times 1, which is 1 minus 2/3, which is 1/3. So the probability that x is less than y is just 1/3. Alright, now let's compute a probability that involves only one of the random variables. Let's find the probability that x is less than some value, let's say a. So this is the integral. We'll get rid of all of the y's. The integral as y goes from 0 to infinity. And the integral of that as x goes from 0 to a. Alright, now the inside integral here, oops, we're integrating dy first, and then dx after. So the inside integral except for this constant e to the negative x is just going to be 1. This is all 1. That dx. Alright, and this is negative e to the negative x evaluated from 0 to a, which is negative e to the negative a minus negative e to the negative 0, which is minus e. Let me write 1 first. E to the negative 0 is 1. 1 minus e to the negative a. I guess that's, we could write that as 1 minus 1 over e to the a. I don't know which is nicer. So that's a good enough expression for this. It's the probability x is less than a. Now let's find the marginal density functions just for x and just for y. So f sub capital X of x is what we get if we integrate f of xy. If we integrate out all the y's, so we've got the integral from, as y goes from 0 to infinity in this case, 2e to the minus 2y, e to the minus x I might as well put on the outside, dy, and then this integral is 1, so we just get e to the minus x. So that's the marginal density of x. And then if we do the same problem for the marginal density of y, we'll integrate out all of the x's. And I might as well pull the 2e to the minus 2y out because that doesn't have any x's in it. But we know that this integral is just 1. So we get 2e to the minus 2y. Now these are sort of interesting answers because the function we started with was the product of 2e to the minus 2y and e to the minus x. That doesn't always happen, that f of xy equals the marginal density of x times the marginal density of y, but it is in this case. So f of xy equals the marginal density of x times the marginal density of y. So again, that doesn't always happen. We'll have to look at this phenomenon more closely in another lesson. The end.